For centuries, humanity has gazed upward, toward a night sky filled with silent questions. From the first time a spark of firelight reflected in a cave dweller's eyes, we have wondered, what lies beyond the horizon of our world? That ancient question has never left us. It has evolved from myth to mathematics, from prayer to propulsion, but it has never stopped calling. Today, in an age when our machines sail between planets and our telescopes stare across billions of light years, that call has become louder than ever. The sky above us is no longer a mystery we merely admire. It is a frontier we are beginning to cross. And with each discovery, each image, each signal, each whisper of data from the void, our understanding of the cosmos deepens, and yet, paradoxically, the mystery only grows. The solar system, once thought to be the entirety of existence, is now our backyard. Its planets, moons, comets, and asteroids were once distant lights in the heavens, mere points of brightness mistaken for gods. Now, they are worlds with histories, storms, oceans, and secrets of their own. But beyond their beauty lies a deeper story, a story not only of planets and physics, but of us. Because to explore the solar system is, in truth, to explore the origins of life itself. In the last half-century, we have done what no generation before us could even dream of. We have walked upon another world. We have watched our spacecraft dive through alien atmospheres, drift beside frozen moons, and send back portraits of worlds that had waited in silence for billions of years. Each mission, Voyager, Galileo, Cassini, Curiosity, New Horizons, has been more than an engineering triumph. It has been a philosophical revelation. For the first time, we are witnesses to creation itself, to how planets form, how they die, and perhaps how life begins. Yet, amid all our progress, one question continues to haunt the human imagination. Are we alone? The more we learn about the diversity of worlds around our sun, the more we realize how delicate and improbable our own existence truly is. From the infernal heat of Venus to the icy plains of Pluto, from the volcanic fury of Io to the silent seas of Titan, each celestial body tells a different version of the same cosmic story, a story of matter, energy, and the persistent possibility of life. But exploration is not only about discovery, it is about reflection. As our robotic emissaries traverse the solar system, they are also revealing something profoundly human, our desire to understand, to reach beyond, to see. Every photograph of a distant planet, every faint transmission across the darkness, is an echo of that first question whispered under ancient skies. What lies beyond? This journey of planets, of machines, of minds, is the story you are about to hear. It begins not on some distant world, but here, on the pale blue sphere we call home. From this single point of light, we have built a window into the cosmos. Through it, we watch the sun's radiant power, the moon's quiet companionship, and the restless motion of worlds that orbit in eternal rhythm. And through that same window, we begin to see our own reflection, small, fragile, and yet immeasurably curious. As we stand at the threshold of interplanetary exploration, one truth becomes clear. The universe is not a distant place. It is the environment we already live in, the vast context of our existence. The story of the solar system is our story, written in dust and flame, in light and shadow, in questions that stretch across eternity. This is not just a tale of science. It is a chronicle of wonder, a voyage through time, space, and imagination. And as we look once more toward the infinite horizon, one question remains, the same one that has echoed since the dawn of humanity. What lies beyond the next world? Part 1. The first glimpse. When humanity reached beyond Earth, in the early years of the 20th century, the stars still belonged to myth. The moon was a poetic companion, not a destination. Mars was a canvas for imagination, painted with canals and civilizations that never were. The planets shone brightly above, but they were unreachable. Too far, too cold, too silent. Humanity's world ended at the edge of the atmosphere. Beyond that thin veil of air lay the great unknown, space. Then, in the middle of the century, everything changed. With the invention of the rocket and the birth of spaceflight, the sky, once a barrier, became a doorway. When a slender metal craft named Sputnik pierced the air in 1957, it carried not only radio signals but a message to every mind on Earth. The cosmos was open. For the first time, humanity had reached beyond its cradle. The horizon had moved. That moment marked the beginning of a new age, the age of exploration reborn in the vacuum of space. Nations raced to the heavens not only for power and prestige, but for knowledge. Astronomers who once peered through glass lenses now looked through electronic eyes aboard satellites and probes. What they saw would change everything we thought we knew about our solar system. The first images from orbit were ghostly and grainy, black and white photographs of Earth's curved limb, a fragile crescent hanging in darkness. Yet even those primitive pictures carried an overwhelming revelation. Our world was small. The vastness of space dwarfed it into a shimmering island, adrift in an endless sea. For scientists and dreamers alike, this perspective shifted everything. The cosmos was no longer abstract. It was real, reachable, and waiting. In the following decade, the race to explore accelerated beyond imagination. In 1961, Yuri Gagarin became the first human to orbit the planet, circling Earth in a voyage that lasted just 108 minutes but redefined human destiny. Only 8 years later, Neil Armstrong stepped onto the surface of the moon, his voice trembling slightly as he declared a giant leap for mankind. With that step, the ancient dream of touching the stars became a memory carved into history. Yet even as humanity turned its gaze skyward, a quieter revolution was unfolding, one driven not by astronauts, but by machines. These early robotic explorers would become our eyes and hands across the solar system, venturing into places no human could survive. They were, in a sense, extensions of ourselves, crafted with precision, launched with hope, guided by curiosity. The first of these emissaries to make history was Luna 3, a Soviet spacecraft launched in 1959. It did not carry a crew, but it carried a camera. As it looped around the far side of the moon, it captured what no human had ever seen, the hidden hemisphere forever turned away from Earth. The images were blurred, yet monumental, craters and plains that had been invisible since time began. For the first time, the moon had given up one of its oldest secrets. Soon after, NASA's Mariner probes followed, charting paths toward Venus and Mars. They were small, fragile, and slow by cosmic standards, but their impact was immeasurable. Each photograph they returned was a revelation. Venus was not the twin of Earth that many had imagined, but a suffocating inferno of heat and acid clouds. Mars, once thought to be covered in vegetation, was instead dry, barren, and pockmarked by ancient scars. It was a sobering discovery, yet it deepened the mystery. If life existed nowhere else, why had it flourished here? By the 1970s, our mechanical explorers had grown bolder. Pioneer and Voyager were sent beyond the inner planets, carrying instruments capable of measuring magnetic fields, radiation, and the faint whispers of cosmic dust. When Voyager 1 sent back its first color images of Jupiter's storm-laden surface, humanity saw the solar system not as a series of points in the sky, but as a vast, dynamic family of worlds, each alive in its own way. It was through these missions that the idea of cosmic perspective truly took hold. The solar system, once a distant concept, became a place, a landscape of wonders and violence, beauty and desolation. The sun's power, the planet's diversity, and the silent ballet of moons and rings. All of it became tangible through the lens of our robotic ambassadors. But perhaps the greatest transformation was not technological, but philosophical. In exploring other worlds, we began to see our own more clearly. The thin blue atmosphere that sustains every living creature appeared, from space, as a fragile film against the endless void. The Earth was not the center of the universe. It was a participant in a grander cosmic story. From that first radio ping from Sputnik to the golden discs of Voyager, humanity's exploration of space became more than a scientific endeavor. It became a mirror. Each mission reflected our deepest desire to understand our origins, our purpose, and our place in the infinite expanse. And as the probes continued outward, crossing the boundaries of Earth's gravity, one truth echoed through every signal, every image, every discovery. We are not confined to this world. We are a species built to explore. Part 2. Windows to the Planets. The birth of robotic vision. By the dawn of the space age, humanity had learned to look upward with instruments of breathtaking precision. Telescopes had already opened our eyes to distant galaxies and dying stars, but they could never bridge the gap between our world and the mysterious spheres that wandered across the night sky. Even the most powerful observatories were prisoners of Earth's atmosphere, their vision blurred by air and distance. What we needed was not a better telescope, but a new kind of explorer. That explorer was a machine. In the early 1960s, the first generation of robotic spacecraft transformed the way we saw the solar system. These were not the grand starships of science fiction, but compact messengers of metal, silicon, and courage. They were the eyes of humanity, hurled into the void to bring back visions from places we had only imagined. Their names, Mariner, Venera, Pioneer, would become the first words in a new vocabulary of exploration. The idea was audacious, to send cameras and sensors across millions of kilometers through radiation belts, solar storms, and planetary gravity, and to expect them to survive. Many did not. Some probes failed before they even cleared the launch pad. Others vanished into silence. But every failure carried a lesson, and every success redrew the map of what was possible. In 1962, NASA's Mariner 2 became the first spacecraft to successfully fly past another planet, Venus. It found not a paradise of jungles, as once imagined, but a hellish furnace cloaked in dense clouds. The surface temperature soared above 460 degrees Celsius. The pressure was crushing, the air toxic. Venus, our supposed twin, was in truth a cautionary tale, a world consumed by the very heat it trapped. Just 3 years later, Mariner 4 passed by Mars. Its camera, primitive by modern standards, snapped 21 photographs that forever shattered illusion. Gone were the dreams of canals and alien cities. The images revealed a dead world, cratered and ancient, its thin atmosphere unable to shield it from the relentless impact of time. It was a heartbreak for some, but a revelation for science. The universe, it seemed, was not built for comfort. It was built for survival. Meanwhile, across the Atlantic, the Soviet Union pursued its own visions of exploration. The Venera missions dared to descend through the suffocating clouds of Venus, sending back ghostly glimpses of a landscape that glowed with infernal light. Their cameras captured rocks and plains distorted by pressure so immense that it would crush steel. The images lasted only minutes before the probes melted and fell silent, but those minutes rewrote human understanding of planetary extremes. And then came the age of the giants. In 1973, NASA's Pioneer 10 became the first spacecraft to fly beyond the orbit of Mars and approach Jupiter. What it found was a world unlike any other, a planet so massive it could swallow all the others and still have room to spare. Its storms raged larger than Earth itself, and its radiation belts screamed with invisible fury. But from that chaos emerged beauty, swirls of color, rings of faint dust, and the first hints of the complex magnetic field that would later be studied by Voyager and Juno. Voyager 1 and Voyager 2, launched in 1977, were the culmination of everything we had learned. Each carried cameras capable of capturing the planets in vivid color and detail. Their trajectories were calculated to perform a rare cosmic dance, a grand tour that would let them visit Jupiter, Saturn, Uranus, and Neptune in a single journey, using the gravity of one planet to slingshot to the next. When Voyager 1 reached Jupiter, its images stunned the world. The planet's turbulent atmosphere was alive with storms and lightning, its moons revealed as complex worlds of ice and rock. Then, as the spacecraft swept past Saturn, it captured the ethereal rings in perfect clarity, a structure of breathtaking elegance, made of ice, dust, and time. But perhaps the most profound moment came not from what the Voyagers saw, but from what they left behind. In 1990, as Voyager 1 drifted beyond the orbit of Neptune, astronomer Carl Sagan persuaded NASA to turn its camera back toward Earth. From 6 billion kilometers away, the spacecraft captured a single pale dot suspended in a shaft of sunlight. That image, the pale blue, became one of the most powerful symbols in human history. On that speck, every life that ever lived, every triumph and tragedy, every king and peasant, every mother and child, all of it existed together on a grain of dust suspended in a sunbeam. It was a moment of cosmic humility. Through the eyes of our robotic explorers, the solar system had become more than a collection of distant orbs. It was a living gallery, a place of storms and silence, of heat and ice, of ancient violence and fragile beauty. Each image, each transmission, each faint echo from across the void was a new window, one that did not just show us other worlds, but reflected our own humanity back at us. And as technology advanced, those windows grew sharper, clearer, more daring. Cameras capable of capturing ultraviolet light, infrared heat, and the ghostly glow of magnetic fields began to reveal layers of reality no human eye could ever see. The solar system was no longer just a spectacle, it was a laboratory, a place where we could test the limits of science, imagination, and endurance. Yet, as the images poured in and our understanding deepened, a new realization began to emerge, one that would redefine our place in the cosmos. If such diversity and wonder existed within a single star's family, what might await us among the countless billions beyond? Part 3. The fire at the center. Understanding the sun, at the heart of our solar system, burns a colossal engine of creation and destruction. The sun. It is both familiar and alien, so constant that we forget its power, so near that we mistake it for simplicity. But the sun is neither gentle nor simple. It is a star, a roaring sphere of plasma so immense that it contains 99.8% of all the mass in the solar system. Without it, every planet, moon, and fragment of ice would drift silently into the dark. For our ancestors, the sun was divine. Its rise marked the rhythm of life. Its disappearance brought fear and uncertainty. Ancient civilizations built temples, monuments, and calendars around its motion, sensing that in its warmth lay the secret of existence. In Egypt, it was Ra, the giver of life. In Greece, Helios, the eternal charioteer. To the Maya, it was a god who demanded reverence and awe. They were not wrong to worship it, but what they could not have imagined is the true nature of that celestial fire. The sun is not flame at all, it is fusion. Deep within its core, hydrogen atoms are crushed together by unimaginable pressure, fusing into helium and releasing energy in the process. Every second, the sun converts over 4 million tons of matter into pure light and heat. It is the most efficient power plant in the known universe, and it has been burning steadily for more than 4.5 billion years. Yet even the sun has its moods. To the unaided eye, its light seems smooth and unwavering. But when Galileo first turned his telescope toward it in the early 1600s, risking his vision to glimpse the truth, he saw something astonishing: dark blemishes drifting across its surface. Sunspots, they appeared and vanished in cycles, hinting at an invisible rhythm within the star itself. Galileo had stumbled upon the heartbeat of the sun centuries later. With the advent of modern astronomy, those dark spots revealed their secret. They are the visible scars of magnetic storms, regions where the sun's magnetic field twists and buckles, briefly suppressing the flow of heat from below. Around these sunspots, immense loops of plasma arc into space, carrying energy millions of times greater than the most powerful lightning bolt on Earth. Every 11 years, this magnetic cycle intensifies. The sun's surface becomes restless, its corona, the outermost layer, blazes with flares and eruptions. Vast clouds of charged particles are hurled across space in violent coronal mass ejections. When those particles reach Earth, they collide with our planet's magnetic field, painting the skies with auroras and occasionally wreaking havoc on satellites and power grids. It is a cosmic reminder that our world, for all its beauty, lives in the atmosphere of a star. The first spacecraft to truly study the Sun from space, missions like Skylab, SOHO, and Parker Solar Probe, have revealed just how complex and dynamic it truly is. Using ultraviolet and X-ray instruments, they have shown us structures invisible to human eyes. Arches of fire tens of thousands of kilometers high, rivers of magnetic energy, and shockwaves that ripple through the solar wind. This wind, a constant flow of charged particles, streams outward from the Sun in all directions, shaping a vast bubble known as the heliosphere. Every planet, every comet, every grain of dust in our solar system exists within this invisible envelope. Beyond it lies the interstellar medium, a realm of cosmic radiation and frozen starlight. The heliosphere is our cosmic shield, forged by the Sun itself. Understanding the Sun is not only an act of curiosity, it is an act of survival. Modern civilization depends on its stability. Our satellites, communications, and even power grids are vulnerable to solar storms. In 1859, a massive eruption known as the Carrington event sent electric currents surging through telegraph lines, sparking fires and shocking operators. If a similar event occurred today, it could cripple global infrastructure in seconds. And yet, for all its danger, the Sun is also our cradle. Its energy sustains every leaf that grows, every ocean current that moves, every breath we take. The photons that warm your skin on a summer day began their journey in the Sun's core over 30,000 years ago, bouncing and scattering through dense layers of plasma before escaping into the void and traveling across 150 million kilometers to reach you. It is humbling to realize that everything on Earth, every mountain, ocean, and living cell, owes its existence to that single furnace of fusion. The iron in our blood, the calcium in our bones, the carbon in our cells, all forged in stars like the Sun that lived and died before ours was born. In studying the Sun, we are not merely understanding a ball of gas. We are tracing the lineage of energy itself, from the nuclear reactions at its heart to the soft warmth that nurtures a seedling on Earth. The same flow of power connects us all. When we look toward the Sun, we are seeing not just the source of life, but the very engine that binds the solar system together. Its gravity holds the planets in their orbits. Its light defines the measure of time. Its storms whisper across the cosmos, carrying the echo of our star's restless soul. And though our eyes cannot bear to look directly at it, the truth remains. Everything we are is a reflection of that fire. We live within a star's embrace. Part 4, Worlds of Stone, the story of the rocky planets in the silent clockwork of the solar system. For small worlds circle close to the Sun, bound by gravity and heat. They are Mercury, Venus, Earth, and Mars, the inner planets, the rocky ones. To the human eye, they seem like siblings born of the same cosmic cloud. But look closer, and each reveals a personality as distinct as any world could have. One scorched, one suffocated, one alive, and one frozen in time. Their story begins over 4.5 billion years ago, when the Sun was young and the solar system was chaos. Swirling gas and dust collided, merged, and shattered again, forming a disk of matter orbiting the newborn star. Within this disk, grains of dust clumped into pebbles, pebbles into boulders, and boulders into protoplanets. A slow and violent birth written in collisions. Closer to the Sun, where heat drove off lighter gases, only the heavy elements, iron, silicon, magnesium, remained. Out of this crucible, the rocky planets were forged. Mercury, the survivor Mercury, smallest and fastest of the planets, is a world of extremes. By day, its surface sears at more than 400 degrees Celsius. By night, it plummets to minus 180. It is a planet with no air to soften the Sun's fury, no atmosphere to hold its warmth. For centuries, it was a mystery, little more than a wandering speck in the dawn sky. Then, in 1974, NASA's Mariner 10 flew past, revealing a landscape battered and ancient, a world that looked eerily like our moon. But Mercury was not what it seemed. Later missions, like Messenger, showed us a dense, metallic planet with a vast iron core, one that makes up nearly 3/4 of its mass. Scientists believe that long ago, a cataclysmic collision may have stripped away most of its rocky crust, leaving behind the heavy heart that remains today. Its surface is scarred by wrinkles, cliffs hundreds of kilometers long, evidence that the entire planet shrank as it cooled, squeezing its crust like a withering fruit. Mercury is a relic, a survivor from an age when the solar system was young and violent. Its silence is not emptiness, but endurance. Venus. The inferno next in line is Venus, Earth's twin in size, but not in spirit. Wrapped in a suffocating veil of carbon dioxide and sulfuric acid, Venus is the very definition of hostile. Its clouds reflect sunlight so brilliantly that it shines as the brightest planet in our night sky. Yet beneath that beauty lies a furnace of unimaginable heat. At 460 degrees Celsius, its surface is hot enough to melt lead. The air pressure there is 90 times that of Earth's, enough to crush a human explorer in moments. For centuries, Venus was imagined as a paradise, perhaps a world of oceans and jungles hidden beneath its clouds. Then came the truth. In the 1970s and 80s, the Soviet Venera probes descended into that poisonous atmosphere and survived only minutes before being destroyed. But in those fleeting moments, they revealed a landscape of shattered plains and volcanic domes, glowing orange in the dim light. Radar mapping later showed a world reshaped by massive eruptions and lava flows, a planet that might still be active today. Venus is a warning written in sunlight, a world undone by its own greenhouse effect, proof that a planet's fate can turn on the chemistry of its air. It shows us what can happen when heat and pressure conspire against habitability, a mirror held up to Earth's possible future. Earth, the living exception, and then there is Earth, the oasis, a planet of oceans, forests, and storms, of magnetic fields and moving continents, of life. Its atmosphere, thin as breath, is perfectly balanced to sustain liquid water, the one ingredient that separates the living from the lifeless. For billions of years, Earth has been the crucible of biology, a place where chemistry learned to dream. Every element on our planet, the iron in our blood, the calcium in our bones, the oxygen in our lungs, was forged in ancient stars and recycled through countless generations of worlds. Yet somehow, on this one world, those elements found a way to organize, replicate, and evolve. Life transformed the air, the land, and even the shape of the planet itself. The blue and green hues that make Earth so distinctive from space are not mere colors. They are the signatures of living systems in motion. Mars. The frozen echo beyond Earth lies Mars, smaller, colder, but hauntingly familiar. It is a world of red deserts, colossal volcanoes, and canyons that stretch beyond imagination. Once, Mars was thought to be alive, a planet of canals and civilizations. Now we know it differently, but not less wondrously. The first flybys in the 1960s showed a desolate surface, dry and cratered. Yet the story did not end there. As the decades passed, new missions revealed evidence that Mars once had rivers, lakes, even oceans. Dried riverbeds snake across its plains. Minerals that form only in water are scattered across its soil. Beneath its rusty surface, ice lies buried, perhaps even liquid water locked deep below. The more we learn, the more Mars feels like a frozen echo of Earth's past. It may once have been warm enough to host life, perhaps microbial, perhaps fleeting. If so, the evidence might still rest beneath its surface, waiting for us to uncover it. For worlds, one origin together, these four planets form a story of evolution and contrast, the delicate line between creation and catastrophe. All were born from the same materials, orbiting the same sun, yet their destinies diverged wildly. Gravity, distance, atmosphere, and time shaped each in unique ways. Mercury is the remnant of violence, Venus the victim of its own heat, Earth the sanctuary, Mars the memory of what could have been. They remind us that habitability is not guaranteed. It is a cosmic accident, a momentary harmony of conditions that could vanish as easily as it appeared. And as our robotic explorers continue to roam among them, collecting dust and data, one truth grows ever clearer. To understand these worlds is to understand our own, for the same forces that shaped them still shape us. Part 5: Water, Atmosphere, and the Search for Life among all the mysteries of the cosmos. One element threads through the story of every world we have ever explored: water. It is both ordinary and miraculous, abundant and rare. On Earth, it flows through every vein of life. Elsewhere, it hides in shadows, freezes in silence, or escapes into the void. To find water is to find possibility. To follow it is to follow the story of life itself. When scientists look across the solar system, they see one question shimmering beneath every crater, every ice field, every drifting cloud. Where can life exist? And wherever that question is asked, the search begins with water. The breath of a world and atmosphere is the skin of a planet, invisible, fragile, and vital. It traps warmth, carries sound, and shapes weather. Without it, even the most promising world becomes a barren rock. Yet atmospheres are not eternal. They are sculpted by sunlight, gravity, and time. Mercury, too close to the sun, lost its air long ago. Venus drowned in its own gases, smothered by carbon dioxide. Mars, lighter and colder, once had an atmosphere thick enough to support rivers and rain. But over billions of years, its magnetic field faded, and the solar wind stripped the air away. What remains is thin as a whisper, enough for dust storms, but not for oceans. On Earth, everything is different. Our magnetic shield guards the atmosphere, our oceans regulate temperature. Here, water and air dance in perfect rhythm. Rain falls, rivers carve valleys, clouds drift, and life flourishes. The balance is delicate, and it has endured for 4 billion years, long enough for life to evolve from single cells to civilizations. The clues on Mars, though barren, still holds echoes of that lost balance. Satellite images reveal river deltas frozen in stone, ancient shorelines curving across dusty plains, and minerals that could only have formed underwater. Even the polar caps gleam with layers of frozen water and carbon dioxide, changing subtly with the seasons. When NASA's Spirit and Opportunity rovers rolled across the Martian surface, they discovered tiny mineral spheres, blueberries of hematite, that could only have formed in liquid water. Later, the Curiosity rover drilled into ancient rocks and found clay, once soaked and altered by long-vanished streams. And Perseverance, still traversing the Jezero crater today, explores what was once a river delta, the fossil remains of a lake that may have sheltered life. Beneath the planet's rusty dust, radar hints at buried ice, and perhaps pockets of salty liquid water that persist even now. If microbes ever lived on Mars, traces of them could still be waiting, fossilized in the soil or sleeping beneath the permafrost, dreaming of a time when their world was blue. The frozen oceans beyond farther from the sun, the search for water takes us into colder realms, places where the heat of sunlight fades, yet the potential for life may still burn beneath the ice. At Jupiter's moon Europa, the surface is a frozen crust, cracked and streaked like shattered glass. But beneath it, evidence points to an ocean larger than all of Earth's combined. A deep, dark sea kept liquid by tidal heat from Jupiter's immense gravity. Plumes of vapor occasionally burst through its icy shell, venting material from the ocean below into space. Those plumes are chemical invitations, hinting that Europa may be one of the best places to search for extraterrestrial life in our solar system. Saturn's moon Enceladus offers an equally tantalizing mystery. Its south pole erupts with fountains of water vapor and ice particles, forming a shimmering halo around the moon. When the Cassini spacecraft flew through those geysers, its instruments detected organic molecules, the building blocks of life. Beneath the ice, Enceladus hides a global ocean heated by the moon's inner tides, a potential cradle for biology in the dark. Even Titan, Saturn's largest moon, challenges our imagination. There, Lakes and rivers of liquid methane flow under a thick orange atmosphere. It is far too cold for water to exist as a liquid, yet methane plays the same role, cycling between gas, liquid, and solid just as water does on Earth. Titan's chemistry may represent an alien version of habitability, one where life could arise from elements utterly foreign to us. The chemistry of hope in every case. Mars, Europa, and Enceladus. Titan scientists follow the same simple logic. Where there is water, there may be energy. Where there is energy, there may be chemistry. And where chemistry persists, life might find a way. Life, as we know it, is astonishingly adaptable. On Earth, microbes thrive in boiling acid, in the darkness of the deep ocean, even inside radioactive rock. If life can exist there, why not beneath the ice of Europa or in the methane rains of Titan? Each discovery tightens the thread that connects these worlds to us. They are not isolated realms, but chapters in a single cosmic story, the story of how the universe experiments with life. The same ingredients that shaped Earth's oceans exist everywhere: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. The universe, it seems, is generous with the ingredients of life. It is the conditions that are rare. The eternal question, and so, across decades of missions and countless billions spent, the question remains: are we alone? Every signal we send, every rover we land, every probe we launch into the darkness seeks not just scientific data, but meaning. We are searching for reflection, another spark of consciousness beneath an alien sky, another world that dared to begin the same story we did. Perhaps one day, a robotic arm will scoop a sample from a frozen sea and find fossilized microbes that lived and died billions of years ago. Perhaps a future astronaut will stand beneath a Martian sunset and watch dust settle over an ancient riverbed. Or perhaps we will never find another living thing, and instead realize that life, for now, is Earth's most extraordinary experiment. Either way, the search changes us, because in seeking others, we begin to understand ourselves, how fragile we are, how improbable, how deeply connected to every drop of water in the cosmos. For life, it seems, is not a miracle of Earth. It is a possibility of the universe. And wherever water flows, the universe may yet remember how to dream. Part 6. The Moon and the Making of a World. Every night, our nearest neighbor rises quietly above the horizon, a pale guardian, casting its cold light across oceans and deserts alike. For as long as humanity has existed, the moon has been our companion, our calendar, our mystery. But it is far more than a silent ornament in the sky. Without the moon, Earth itself would not be what it is. It is no exaggeration to say that the story of our planet, its tides, its climate, even its life, cannot be told without the moon. For centuries, philosophers and scientists pondered the moon's origins. Some imagined it had formed alongside Earth. Others believed it had been captured by our planet's gravity long after both had cooled. But as the Apollo missions returned samples of lunar rock in the late 1960s and early 70s, a new picture began to emerge, one forged not from speculation, but from evidence. The giant impact rocks brought back by Apollo 11, 12, and 17 revealed that the moon and Earth share a striking chemical similarity, almost as if they were made from the same material. Yet the moon was strangely depleted in volatile elements, substances that would have vaporized under extreme heat. That clue pointed to a dramatic conclusion. The moon was born from fire. According to the prevailing giant impact hypothesis, some 4.5 billion years ago, when the Earth was still young and molten, a planet-sized object, roughly the size of Mars, struck it at a glancing angle. The collision released more energy than any event in the planet's history, melting rock and flinging debris into orbit. Out of that orbiting chaos, gravity sculpted the fragments into a single body, our moon. For weeks, the newborn moon glowed red-hot in the sky, while molten rock oceans spread across its surface. Gradually, it cooled, its crust solidified, and volcanic plains, the Lunar Maria, formed as magma welled up from below. The impact reshaped Earth too, giving it its tilt and seasons. It also stabilized Earth's rotation, slowing its day from 6 hours to the 24 we know today. A planet's guardian, that stabilization may have been critical for life. Without the moon, Earth's axis would wobble chaotically over time, plunging the planet into extreme climate swings. The steady gravitational pull of the moon has kept Earth's tilt, and thus its seasons, remarkably stable for billions of years. Our tides, too, are born of its influence. Twice a day, the moon's gravity tugs at the oceans, stirring nutrients, shaping coastlines, and perhaps even influencing the rhythms of life's earliest evolution in tidal pools. Every creature that swims in the sea, every wave that laps the shore, every pattern of migration and reproduction tied to lunar cycles, all owe their existence to that distant sphere. The moon does not simply orbit Earth. It shapes it, breath by breath, tide by tide. The marks of time the moon's face, pocked and cratered, is a record of cosmic history. With no atmosphere, no weather, and no water to erode its scars, every impact remains preserved, a fossil archive of billions of years of bombardment. By counting and dating those craters, scientists have reconstructed the solar system's violent youth, a time when asteroids and comets rained upon all the inner planets. The same impacts that scarred the moon also struck Earth, though wind, water, and life have since erased most of the evidence here. When astronauts looked upon the moon during the Apollo missions, they stood upon a time capsule, a window into the earliest days of planetary formation. Beneath their boots lay dust older than any mountain, rock melted by collisions that predate the continents themselves. The moon, silent and still, holds the story of our beginnings. The human connection yet beyond science. The moon has always touched something deeper in the human spirit. It has inspired poetry, art, and myth in every culture, from the ancient Sumerians who tracked its phases to mark time, to the Chinese legends of Chang'e and her immortal journey. It is a symbol of distance and intimacy, of longing and reflection. When Neil Armstrong stepped onto its surface in 1969, he carried not only technology but millennia of dreams. In that moment, humanity's oldest myth became a memory. The first footprints on another world did not just mark achievement. They marked belonging. For the first time, a living species had crossed the gulf between worlds and looked back upon its home. The view from the moon, Earth suspended in darkness, small and fragile, changed us forever. That image, the Earthrise captured by Apollo 8, reminded us that home is not boundless but precious, a blue oasis in a sea of void. The return and the future decades later, the moon remains our nearest gateway to the cosmos. Robotic missions now map its minerals, its poles, and its hidden ice. Beneath the shadows of craters near the lunar South Pole, frozen water waits, untouched for eons. That discovery has reignited our ambition to return, not merely to visit, but to stay. NASA's Artemis program, along with international partners, aims to build a sustained presence on the moon, a base for exploration, science, and eventually, as a stepping stone to Mars. Future astronauts may drink the melted ice of lunar craters, grow food in regolith-based greenhouses, and watch the Earth rise every day from a new world. But the moon's importance will never only be practical. It is symbolic, a constant reminder that our story is one of connection. Formed from Earth's own body, the moon is both child and companion, the witness to our past and the guide to our future. When we look up at it tonight, we are seeing the echo of an ancient collision, an echo that made life possible. Every tide, every season, every night lit by silver light traces its origin back to that single cosmic event. The moon does not merely orbit Earth, it defines it. It is the quiet architect of balance, the silent twin that made our world whole. And as humanity prepares to walk upon it again, perhaps we will rediscover what it has always represented, the bridge between what we are and what we might yet become. Part 7. The Outer Realms, giants of gas and ice beyond the orbit of Mars. The solar system transforms. The warmth of the sun fades into a pale glow, and the terrain of rock gives way to a realm ruled by giants. Here, gravity becomes architecture. sculpting vast worlds of gas, ice, storms, and moons beyond counting. These are the titans of the outer solar system: Jupiter, Saturn, Uranus, and Neptune. They are worlds too massive to stand upon, too distant for sunlight to warm, and yet too beautiful to ignore. They are the keepers of the deep. Jupiter, the king of planets. Jupiter, the largest planet in the solar system, is a world so immense it could swallow every other planet and still have room to spare. It is more than a planet. It is a miniature solar system of its own, orbited by over 90 known moons and wrapped in rings of faint dust. When Voyager 1 first approached Jupiter in 1979, humanity's understanding of the gas giant changed forever. What had seemed like soft bands of color in telescopic images turned out to be storms. Vast, violent, and alive. The Great Red Spot, a hurricane larger than Earth, had been raging for at least 4 centuries. Its atmosphere swirled with ammonia clouds, lightning bolts hundreds of miles long, and winds that screamed at 600 kilometers per hour. Beneath those clouds, the pressure grows so immense that hydrogen itself turns into liquid metal. Jupiter has no solid surface, only layers upon layers of gas compressing into exotic matter. Deep within, it hides a core of rock and ice wrapped in metallic hydrogen, generating a magnetic field so powerful it extends millions of kilometers into space. That invisible force traps particles from the solar wind, creating radiation belts that would destroy an unshielded spacecraft in hours. Yet amid that chaos, beauty thrives. The planet's 4 largest moons, Io, Europa, Ganymede, and Callisto, form a miniature system of wonder. Io erupts with volcanoes brighter than any in the solar system. Europa hides an ocean beneath its ice, a world that may shelter life. Ganymede, the largest moon, possesses its own magnetic field. And Callisto, ancient and cratered, is a frozen relic of the early solar system. Together, they tell a story of creation, heat, and endurance. Saturn, the Lord of Rings. If Jupiter is the king, Saturn is the poet, the planet of elegance and mystery. Its golden hues and iconic rings have captivated human eyes for centuries. But the beauty of those rings is also an illusion. They are not solid but composed of countless fragments of ice and rock, ranging from grains of dust to house-sized boulders. Each piece reflects sunlight, forming the luminous halo that defines Saturn's appearance. When Cassini entered orbit around Saturn in 2004, it revealed the rings in unprecedented detail. They are delicate and dynamic, shaped by gravity, by moonlets that carve gaps, by unseen waves rippling through their icy bands. Scientists now believe the rings may be temporary, born of a shattered moon or captured comet, and may one day fade away into the planet's atmosphere. Yet Saturn's majesty extends far beyond its rings. Its atmosphere is striped with pale bands and vast storms. Deep below lies a sea of metallic hydrogen, spinning fast enough to flatten the planet at its poles. And orbiting this gas giant is a family of moons as rich and strange as Jupiter's. Titan, cloaked in a thick orange haze, has rivers and lakes of liquid methane. Enceladus, smaller than some continents, hides a global ocean beneath its icy crust, an ocean that vents geysers of water and organic compounds into space. The Cassini mission's final dive through those plumes provided proof that beneath the ice, chemical reactions are taking place, reactions that could sustain life. In a sense, Saturn is not just a planet. It is a system of worlds, a living laboratory of chemistry and geology where the boundaries between rock, gas, and life blur. Uranus, the sideways world farther still lies. Uranus, pale, distant, and strange. Unlike any other planet, Uranus spins on its side, tilted more than 90 degrees. Its poles take turns pointing toward the sun, giving rise to seasons that last more than 20 Earth years each. The cause of this tilt is likely ancient violence, a massive collision during formation that knocked the planet over. Uranus is an ice giant, composed mostly of water, methane, and ammonia frozen into exotic forms. Its faint blue-green color comes from methane absorbing red light, leaving only the cool hues behind. When Voyager 2 flew past in 1986, it found a world calm to the point of eeriness, featureless, cold, and quiet. But modern telescopes have revealed a hidden dynamism. Storms brewing deep within, rings faint as whispers, and moons that dance in eccentric orbits. For all its calm, Uranus remains one of the least explored and least understood worlds. Beneath its tranquil appearance may lie a complex structure, perhaps layers of slushy oceans, exotic ices, or even diamond rain falling toward the core. Neptune. The wind from the abyss at the edge of the solar system drifts Neptune, the last true planet before the dark frontier. Its deep blue hue hides one of the most violent atmospheres in existence. Winds scream across its clouds at over 2,000 kilometers per hour, faster than the speed of sound on Earth. When Voyager 2 passed by in 1989, it discovered a massive storm, the Great Dark Spot, swirling across the planet's surface. Within it, the atmosphere boiled and rolled with energy, despite receiving only a fraction of the sunlight that warms Earth. This mystery puzzled scientists. How could such a distant, frozen world harbor so much internal heat? The answer may lie within its core, a furnace of pressure and friction that releases energy into the atmosphere. Neptune, like its sibling Uranus, is wrapped in layers of hydrogen, helium, and methane. Its magnetic field is chaotic, tilted and offset from the planet's center, twisting and flickering as it rotates. Among Neptune's moons, one stands out, Triton. Unlike any other large moon, it orbits backward, suggesting it was captured from the Kuiper Belt long ago. Its surface is young and active, with nitrogen geysers that erupt into the thin air, painting dark streaks across the landscape. Triton, like Europa and Enceladus, may also hide an ocean beneath its crust, another potential harbor for life, frozen at the edge of the sun's light. The frontier of the giants, these outer worlds, are not just astronomical curiosities. They are keys to understanding the origins of everything. Their immense gravity shaped the orbits of the planets, captured comets, and flung asteroids across the solar system. Without them, Earth might never have existed in a stable orbit long enough for life to arise. The gas giants are, in a sense, the architects of habitability. They remind us that even in the cold and the distant, there is purpose, that every world, however alien, plays its part in the grand design. In their storms, rings, and moons, we see echoes of creation, the raw mechanics of a universe still in motion. And as our probes continue to drift through their shadows, the giants remain silent, waiting for us to return with better eyes, stronger machines, and the same timeless curiosity. Because somewhere, beyond the reach of sunlight, the story of the solar system continues, and it begins again with these colossal worlds that guard the outer darkness. Part 8. Beyond Neptune. The frozen frontier, past Neptune. Sunlight fades into a dim twilight that never becomes full day. The warmth of the sun, once the engine of life and motion, dwindles to a pale echo. Here begins the outermost frontier of our solar system, a realm of ice, shadow, and silence. It is a place where time moves slowly, where ancient objects from the dawn of creation still drift untouched, and where our understanding of what defines a planet was forever changed. This is the domain of the Kuiper Belt and the scattered icy worlds that lie beyond Pluto, Eris, Haumea, Makemake, and countless others. These frozen remnants are not planets in the traditional sense. They are fossils, fragments of the original material from which the solar system was built. To study them is to peer into the past, to glimpse the blueprint of our celestial home. The discovery of the distant for much of human history, Neptune marked the edge of the known solar system. But in 1930, a young American astronomer named Clyde Tombaugh, working late nights at the Lowell Observatory in Arizona, noticed something faint moving against the stars. It was small, distant, and icy. He had discovered Pluto, the first known world beyond Neptune. At first, Pluto was hailed as the ninth planet, a mysterious outpost in the darkness. For decades, it held that title proudly. But as telescopes improved and more distant objects were found, astronomers realized Pluto was not alone. There were dozens, hundreds of similar icy bodies orbiting far beyond Neptune. Pluto was merely one member of a vast, hidden population. In 2006, after years of debate, the International Astronomical Union redefined the word planet. Pluto was reclassified as a dwarf planet, joining a new family of small icy worlds that populate the Kuiper Belt. For some, it was a demotion. For science, it was a revelation. The discovery meant that our solar system was far larger, richer, and more complex than we had imagined. Pluto, the world of ice and shadow in 2015, after a 9-year journey across nearly 5 billion kilometers, NASA's New Horizons spacecraft flew past Pluto, becoming the first mission to visit the dwarf planet. What it found astonished scientists. Pluto was not a lifeless ball of ice. It was active, alive in its own frozen way. Its surface glowed with plains of nitrogen ice, mountains of solid water, and strange, heart-shaped patterns that hinted at geologic activity. One region, the vast Sputnik Planitia, appeared to be a basin filled with convecting ices, proof that heat still moved beneath the surface. The temperature on Pluto never rises above -230 degrees Celsius. Yet even in that frozen realm, motion and change persist. Its thin atmosphere of nitrogen and methane rises and falls with the seasons, freezing onto the surface when winter comes and vaporizing when sunlight returns. In its faint blue haze, backlit by the sun, New Horizons captured a haunting beauty, a reminder that even at the edge of darkness, worlds can still breathe. Pluto's largest moon, Charon, is locked in a slow dance with its parent. The two worlds orbit a common center of gravity in space, a binary system unlike any other in the solar system. Charon's surface is scarred by canyons and cliffs that dwarf the Grand Canyon, suggesting that beneath its crust once flowed a liquid ocean that froze and cracked as it cooled. Together, Pluto and Charon are a portrait of complexity in miniature, proof that even tiny worlds can evolve, fracture, and surprise us. The Kuiper Belt and beyond Pluto stretches a vast and mysterious region known as the Kuiper Belt, a broad ring of icy bodies extending billions of kilometers from the sun. These objects are relics from the solar system's formation, never swept up into planets or burned away by sunlight. Their orbits are elongated, tilted, and chaotic, influenced by the gravity of Neptune and perhaps even by something unseen beyond. Some of the most intriguing discoveries include Haumea, an egg-shaped dwarf planet spinning so fast that its day lasts only 4 hours. Makemake, a bright red world with patches of frozen methane, and Eris, slightly smaller than Pluto but farther away, whose discovery reignited the debate over what truly defines a planet. And beyond even the Kuiper Belt lies the scattered disk, a region of objects flung outward by the early gravitational chaos of the giant planets. These are the true wanderers, following paths that take centuries or millennia to circle the sun. They are the nomads of the solar system's edge. The whisper of the Oort cloud farther still, 100, 1,000 times farther, lies something even more elusive, the Oort cloud. It has never been seen directly, but its presence is known through the comets that occasionally visit the inner solar system. The Oort cloud is believed to be a vast sphere of icy bodies surrounding the sun, stretching halfway to the nearest stars. These ancient comets are time capsules, preserving the original ingredients of the solar system: water, carbon compounds, and frozen gases. When disturbed by passing stars or galactic tides, some are sent inward, igniting into glowing comas as they approach the sun. Every comet that blazes across our skies is a messenger from that distant frontier, a brief, burning echo of creation. A boundary and a beginning in 2018, Voyager 2 crossed the heliopause, the boundary where the sun's influence ends and interstellar space begins. Its twin, Voyager 1, had crossed earlier, becoming the first human-made object to leave the solar system. Together, they now drift in the eternal night, still whispering faint signals back to Earth. What lies beyond their reach remains unknown. Perhaps there are more undiscovered planets lurking in the shadows. A Planet 9, hinted at by the strange alignments of distant orbits. Or perhaps the solar system simply fades, grain by grain, into the dust between the stars. But one truth endures. The frontier is not a line, but a horizon. The further we go, the further it recedes. And in that endless pursuit, we are reminded that exploration is not about reaching the end. It is about expanding the circle of the known. The frozen frontier beyond Neptune is not emptiness. It is memory, the solar system's original self, preserved in ice. Every distant object that we discover, every comet that returns to the light, carries with it a piece of the story that began more than 4 billion years ago. And as we listen for the faint heartbeat of Voyager, now beyond the warmth of our sun, we are hearing something more than a signal. We are hearing the echo of our own curiosity, the sound of humanity reaching, still, for the edge of the known sky. Part 9. The Interplanetary Web, Gravity, Orbits, and Cosmic Architecture. The solar system is often imagined as a collection of isolated worlds circling a star, each following its own quiet path. But this image is incomplete. In truth, the solar system is not a series of separate orbits. It is a single, interconnected structure, woven together by the invisible threads of gravity. Every planet, moon, and asteroid participates in a vast, cosmic dance choreographed by the sun. The result is not chaos, but order, a dynamic harmony that has endured for billions of years. The music of motion, the laws governing that dance were first glimpsed by Johannes Kepler in the early 1600s. Watching the heavens through imperfect instruments, he noticed patterns, planetary motions that followed mathematical grace rather than random chance. His discovery, that planets move in ellipses with the sun at one focus, revealed a hidden rhythm in the cosmos. A few decades later, Isaac Newton uncovered the force behind that rhythm: gravity. With his law of universal gravitation, Newton showed that the same invisible pull that draws an apple to Earth's surface also holds the moon in its orbit and keeps the planets tethered to the sun. For the first time, the universe became understandable, not through myth, but through mathematics. Every orbit is a balance of two forces: the planet's forward motion and the sun's gravitational pull. Too slow, and a world would spiral inward to destruction. Too fast, and it would drift away into the dark. This delicate balance creates the architecture of the solar system, an arrangement so stable that it has persisted since the dawn of time, yet so dynamic that every moment brings subtle change. The architecture of harmony: if the solar system were a symphony, gravity would be its conductor, and each planet a note in its celestial score. The inner worlds, Mercury, Venus, Earth, and Mars, form the brisk, intricate melody near the sun, where orbits are short and energy is high. The outer giants, Jupiter, Saturn, Uranus, and Neptune, move in slower, deeper tones, their orbits stretching across centuries. Together, they form a composition that resonates across space and time. The distances between these orbits are not random. They follow a rough spacing pattern, known since the 18th century as the Titius-Bode law, a kind of mathematical echo of how the solar system formed from a rotating disk of gas and dust. Although not exact, the pattern hints at a deeper order, one shaped by resonance. Resonance, the invisible connection resonance, occurs when one orbit influences another, locking worlds into rhythm. For example, Pluto orbits the Sun twice for every 3 orbits of Neptune. This 3:2 resonance keeps them from ever colliding, even though their paths cross. The same phenomenon shapes the moons of Jupiter, Io, Europa, and Ganymede orbit in a 1:2:4 resonance that amplifies their internal heat, driving Io's volcanoes and Europa's subsurface ocean. Resonances are the solar system's hidden hand, guiding motion, distributing energy, and maintaining balance. Sometimes they destabilize, flinging asteroids into new paths, or causing entire regions, like the asteroid belt, to remain empty of large bodies. The spaces between Jupiter's gravitational harmonics are visible scars in that belt. The Kirkwood gaps, silent evidence of cosmic order at work. The gravity of giants among all the planets, Jupiter plays the most influential role in shaping the solar system's architecture. Its immense gravity acts as a cosmic shield, deflecting comets and asteroids that might otherwise strike the inner planets. Some astronomers believe Jupiter's presence made life on Earth possible by sweeping away much of the early debris that could have obliterated fragile beginnings. Yet Jupiter is not merely a protector. It is also a sculptor. Its pull stirs the asteroid belt into patterns, captures Trojan asteroids along its orbit, and even tugs subtly on the Sun itself, causing the star to wobble slightly as they both orbit a common center of mass. In this sense, the Sun does not truly sit still at the center of the solar system. It too moves in a slow, looping dance, its motion dictated by the planets it commands. The moons and the microcosm, each giant planet carries its own miniature solar system, complete with moons, rings, and magnetic fields. The relationships among these moons mirror the gravitational web of the larger system. Io's eruptions, Titan's atmosphere, Europa's tides, all are products of gravitational interplay. The same laws that bind planets to the Sun bind moons to their parents, and tides to their oceans. Gravity not only shapes space, it shapes time. A planet's year, a moon's month, a comet's centuries-long journey, all are measures of gravity's pull. Even the precession of Earth's axis, the slow wobble that changes our climate over tens of thousands of years, is a subtle result of the gravitational handshake between Earth, the Moon, and the Sun. Chaos and stability, though the solar system appears orderly, it is not static. Over vast timescales, small shifts accumulate. Planets tug on one another, orbits stretch, tilt, and drift. Asteroids are nudged into new paths. Comets fall inward. Even the shape of Earth's orbit changes slightly over millennia, influencing ice ages and climate. The solar system is not a perfect machine. It is a living system, evolving and reshaping itself in slow, elegant motion. Computer simulations show that even tiny gravitational nudges can have monumental consequences over billions of years. Yet despite this inherent chaos, the overall structure endures. It is a paradox of nature, a system both fragile and resilient, balanced on the edge between order and entropy. A universal blueprint. As we look to other stars, we find that the solar system is not unique. Thousands of exoplanets have been discovered, orbiting distant suns in an astonishing variety of arrangements. Some tightly packed, others widely spaced, some circling two stars, others wandering freely in interstellar space. And yet, among this diversity, patterns emerge. Systems of resonant orbits, gas giants shepherding debris disks, rocky worlds nestled in habitable zones. It seems the architecture of the cosmos follows universal rules. The same laws that shaped our Sun's family shape countless others. In understanding our own solar system, we are deciphering the language of the universe itself. Gravity, that invisible sculptor, does more than hold worlds in place. It writes their stories. It binds the stars into galaxies, galaxies into clusters, and clusters into the grand cosmic web that spans the universe. Here, in our modest solar system, we witness that same principle at work, an echo of the larger universe, scaled to human comprehension. Each orbit, each resonance, each delicate balance is a line in a vast cosmic manuscript. And as our instruments grow more precise, our models more detailed, we begin to see the solar system not as a collection of worlds, but as one interconnected organism, alive with motion, symmetry, and purpose. We are part of that harmony, bound to the same rhythm that guides planets and stars alike. The web that holds the solar system together also holds us. Atoms forged from stardust, minds drawn upward by gravity's eternal call. Part 10. Messages from the void. Comets, asteroids, and cosmic time. Between the grand orbits of the planets lies a vast realm of wanderers, fragments, relics, and messengers from the dawn of time. They are comets and asteroids, the debris left over from creation, drifting through the solar system like ancient ghosts. Each one carries a story written in dust and ice, a message from an era long before Earth had oceans or sky. They are the building blocks of planets, the remnants of collisions, the frozen archives of our cosmic past. And in their silence lies a key to understanding where we came from, and perhaps where we are going. The broken pieces of creation when the solar system first formed, billions of small bodies orbited the newborn sun. Most were swept up into planets or cast into the cold by gravitational encounters. But some survived, trapped between or beyond the orbits of the great worlds. These are the asteroids and comets, the survivors of creation. The asteroid belt, a wide expanse between Mars and Jupiter, is home to millions of rocky fragments. Though once imagined as the remains of a shattered planet, we now know that the belt is a world that never was, a planet that Jupiter's gravity prevented from forming. Every rock there, from dust grains to the 900-kilometer wide series, is a time capsule from the earliest days of the solar system. Asteroids come in many forms. Some are metallic, rich in iron and nickel, perhaps fragments of ancient planetary cores. Others are stony or carbon-rich, filled with organic molecules and minerals that predate Earth itself. The smallest tumble through space in chaotic orbits. The largest maintain their ancient courses, their paths steady and silent. Ceres, the planet that almost was among the asteroids, Ceres stands apart. Discovered in 1801, it was the first object found in the belt and the largest. When NASA's Dawn spacecraft arrived there in 2015, it revealed a world far stranger than anyone had expected. Not a mere rock, but a differentiated body with signs of past geological activity. Bright patches of salt on its surface hinted at briny water once seeping upward from below, freezing in shimmering patterns. There may even be pockets of liquid trapped beneath the crust. Ceres, it seems, is a reminder that even the smallest worlds can hold secrets of habitability, and that water, once again, is the storyteller of life. The wanderers of ice farther out, where the sun's warmth weakens, lie the comets, cosmic travelers born of ice and dust. Most spend their lives in the frozen reaches of the Kuiper Belt or the distant Oort cloud. But sometimes, a gravitational nudge sends one inward, and it awakens. As a comet approaches the sun, its ices vaporize, creating glowing tails that stretch for millions of kilometers. These tails, one of gas, one of dust, always point away from the sun, sculpted by solar wind and radiation. To ancient peoples, they were omens, mysterious intruders in the predictable heavens. Today, we know them as emissaries from the solar system's deep past. Each comet is a pristine relic, unchanged for billions of years. When ESA's Rosetta mission landed its probe Philae on Comet 67P/Churyumov-Gerasimenko in 2014, it discovered that comets carry complex organic molecules, amino acids, carbon chains, and other ingredients of life. The same materials may once have rained down upon the early Earth, seeding the chemistry that would one day breathe. Cosmic impacts. The double-edged gift asteroids and comets have not merely watched history, they have written it. The same collisions that built planets also scarred them. Earth's surface, though reshaped by wind and water, still bears silent witnesses to these encounters, craters that mark moments of cosmic violence. 66 million years ago, one such impact ended the reign of the dinosaurs. A 10-kilometer wide asteroid struck near what is now Chicxulub, Mexico, releasing energy equivalent to billions of atomic bombs. The shockwave ignited forests, darkened the skies, and plunged the world into years of cold. Yet from that destruction came opportunity, the rise of mammals, and ultimately of us. Impacts remind us that life on Earth exists by cosmic permission. The same celestial dynamics that protect us, Jupiter's gravitational shield, Earth's magnetic field, cannot prevent every collision. But they also remind us of life's resilience, its ability to adapt, to recover, and to flourish anew. Modern eyes on ancient stones today, we track thousands of near-Earth objects, asteroids that pass within our planet's orbit. Space agencies around the world monitor them, not out of curiosity alone, but necessity. Programs like NASA's DART mission, which in 2022 successfully altered the orbit of an asteroid by impact, mark humanity's first steps toward defending its home world. For the first time, the species born of stardust learned to shape the course of celestial stone. Meanwhile, missions like OSIRIS-RX and Hayabusa 2 have returned samples from asteroids Bennu and Ryugu, revealing that these small bodies contain both organic molecules and traces of water. Each fragment collected tells a story billions of years old, the chemistry of the early solar system, preserved in dust. Time written in stone, and ice asteroids and comets are more than remnants. They are storytellers of time. The elements within them, carbon, iron, water, silicates, are the same materials that make up our world, but frozen in the state they held before planets were born. To touch one is to touch the past, to feel, quite literally, the beginning of everything. They remind us that the solar system is not static, but alive with motion and memory. Every comet that blazes across the sky is an ancient clock ticking once more. Every meteor that burns in the atmosphere is a spark from creation, briefly rekindled. When we watch these travelers, we are not just witnessing celestial spectacle. We are seeing messages written in cosmic script, letters sent across eons. They whisper that everything, Earth, life, humanity, was once dust drifting through darkness. And perhaps they whisper something else, that creation is not a moment-long past, but an ongoing act, a process that still unfolds, silently, in every collision, every orbit, every grain of interstellar dust. For in the solar system's smallest fragments, we find the universe's oldest story, that from destruction comes creation, and from silence, meaning. Part 11, Echoes of Discovery. Humanity's expanding horizon, every generation inherits the same sky, and yet, each one sees it differently. From the first sailors who steered by starlight to the engineers guiding spacecraft across billions of kilometers, our relationship with the cosmos has been a mirror of our own growth. Every step we take into the solar system reflects a deeper step into understanding ourselves, what we are capable of, what we fear, and what we hope to become. The story of exploration is not just a timeline of missions and milestones. It is the unfolding of curiosity as a force of nature, a human instinct as old as breath. The machines that became our eyes when the space age began, humanity sent machines where we could not go. They became our proxies, our senses stretched across the void. From the early Mariner flybys to the Voyager Grand Tour, these robotic emissaries transformed the unknown into the familiar. By the late 20th century, spacecraft were no longer just explorers, they were scientists. The Galileo mission orbited Jupiter for 8 years, studying its storms and discovering evidence of an ocean beneath Europa's icy surface. Cassini spent over a decade in the Saturnian system, revealing the secrets of its rings and uncovering geysers on Enceladus that still astonish researchers. Meanwhile, the Mars Global Surveyor, Spirit, Opportunity, and Curiosity rovers turned a red dot in the sky into a place we could almost imagine standing upon. With each mission, Mars became less of a mystery and more of a destination. A landscape of valleys, dust devils, and sunsets that glow blue in the thin air. In 2015, New Horizons completed humanity's first reconnaissance of Pluto, transforming a distant speck into a world of mountains and frozen plains. And today, probes like Juno, Lucy, and Europa Clipper continue that legacy, mapping the architecture of the outer planets, tracing the chemistry of the early solar system, and searching for signs of habitability beyond Earth. Each mission, no matter how small, is part of a grand continuity, the widening of the human gaze. The rise of the observatories while machines ventured outward, others turned their eyes inward, or rather upward from home. The Hubble Space Telescope, launched in 1990, gave humanity the ability to see the universe with crystalline clarity. Hovering above the blur of Earth's atmosphere, Hubble revealed the solar system as never before. Storms churning across Jupiter, shadows dancing on Saturn's rings, auroras flickering above the poles of Uranus and Neptune. Yet Hubble also looked beyond, to galaxies billions of light years away, to the edge of time itself. It reminded us that our solar system, vast as it seems, is but one drop in an ocean too immense to measure. In its wake came successors, the James Webb Space Telescope, with its golden mirrors designed to capture the faint heat of creation, and new ground-based observatories capable of seeing exoplanets orbiting distant suns. We no longer study the solar system in isolation, but as one example among countless others. Each observation is a thread tying our story to the broader cosmos. Human footprints in the dust, yet, for all the data and distance, there remains something singular about human presence, the act of standing on another world and calling it real. When Neil Armstrong and Buzz Aldrin walked upon the moon in July 1969, it was not just a technical feat, it was a spiritual one. Two fragile humans, separated from home by the void, left footprints that will outlast every monument on Earth. In that moment, the moon ceased to be myth. It became a memory shared by all humanity. In the decades that followed, human exploration paused, but the dream did not fade. The International Space Station became a bridge between nations, orbiting 400 kilometers above the surface, a laboratory of cooperation and endurance. From that vantage, astronauts witnessed 16 sunrises a day, watching the thin blue arc of Earth's atmosphere flicker with lightning and auroras. From there, the fragility of home is undeniable. Now, humanity prepares to return to the moon, this time to stay. NASA's Artemis missions, in partnership with agencies and companies worldwide, aim to build the first permanent outpost on another world. From its surface, astronauts will gaze not up at the moon, but down at Earth and outward toward Mars. Mars, the next horizon. The dream of Mars has never faded. Every rover, every orbiter, every grain of dust analyzed has been one step closer to a human footprint on the red planet. Engineers now design habitats that could withstand radiation and cold, greenhouses that could grow food in alien soil, and propulsion systems capable of carrying crews across interplanetary space. Private companies have joined the effort, transforming exploration from national ambition into human enterprise. The first footprints on Mars will not just mark discovery. They will mark the beginning of humanity's transformation into an interplanetary species. Mars, for all its desolation, is the logical next step. It is close enough to reach, familiar enough to study, alien enough to humble us. To stand beneath its salmon-colored sky will be to look both forward and backward, to the origins of life and to the destiny of those who seek it. The long view, beyond the planets but even Mars, is only the beginning. Beyond it lie the asteroids, the icy moons, and eventually the frontier of interstellar space. Our spacecraft, Voyager, Pioneer, New Horizons, are already on that path, carrying with them golden records inscribed with humanity's voice, music, and art. They drift silently between the stars, tiny emissaries of consciousness in a vast, indifferent sea. One day, their messages may be found by descendants of Earth or by minds we cannot yet imagine. And if they are, they will tell a simple story, that life arose on a small blue world around an ordinary star, and that it learned to wonder. The legacy of curiosity, every discovery we make reverberates through time. The instruments may fade, the missions may end, but the knowledge remains, adding to a mosaic that grows richer with each passing decade. We have mapped the surfaces of other worlds, traced the breath of comets, and listened to the heartbeat of a star. Yet the most profound discovery has been the realization that we belong to it all. We are not separate from the solar system, we are its children. The same dust that built the planets built us. The same gravity that binds worlds together binds us to them. To explore space is not to escape home, but to understand it more deeply. The solar system is our history book, our laboratory, and our destiny. Each spacecraft that leaves Earth carries not just instruments, but intent, a promise that curiosity will endure. And as the echoes of exploration continue to ripple outward, one thing becomes clear. Humanity's horizon is not a line, but a motion, ever expanding, ever seeking. For in every discovery, there is an echo. And in that echo, we hear not the universe calling to us, but ourselves calling back. We are here. We have seen. We will continue. Part 12, The Age of Connection. Data, discovery, and the living cosmos, the modern age of exploration is no longer defined by rockets alone. It is defined by connection, the invisible web of data that links telescopes, probes, and human minds across the solar system. For the first time in history, our instruments speak to one another, forming a nervous system for an entire civilization. And through that network, the universe is awakening into focus, not as something distant, but as something alive with motion, meaning, and memory. The digital universe, each spacecraft that leaves Earth carries not just sensors and cameras, but voices, signals that flow homeward across millions of kilometers. From the cold plains of Mars to the clouds of Jupiter, data travels as light, encoded in radio waves, captured by great dishes that listen day and night. The Deep Space Network, a trio of massive antenna complexes in California, Spain, and Australia, forms the beating heart of this system. Every transmission is a miracle of precision. A signal from Neptune's orbit, faint as a whisper, arrives as a fraction of a billionth of a watt, yet it carries the weight of discovery. Together, these streams of information form a living archive. Terabytes of images, spectra, and telemetry, all describing the solar system as it truly is, moment by moment. This web of data has transformed exploration into collaboration. A spacecraft orbiting Mars can now relay signals for another rover. Observatories on Earth and in orbit combine their views to create a single, unified image. Artificial intelligence sorts through endless streams of measurements, finding patterns invisible to human eyes. The solar system has become a connected organism, and humanity is its growing awareness. From observation to understanding, science has always been a bridge between curiosity and comprehension. But never before has that bridge been so wide or so fast. In the 21st century, our ability to observe the cosmos has exploded. Telescopes like James Webb, Keck, and ALMA can detect the faintest heat signatures, the chemistry of distant atmospheres, the birth of exoplanets around newborn stars. Data once gathered over years now flows in hours. Supercomputers simulate the formation of solar systems from clouds of gas, tracing every eddy of dust, every collision that shapes a world. At the same time, smaller instruments, backyard telescopes, citizen science projects, even amateur radio antennas contribute to the same global quest. Exploration has become democratic. The universe is no longer reserved for agencies or institutions. It belongs to everyone who looks up. Each byte of data, each pixel of starlight, adds to the same unfolding map. A map not of geography, but of understanding. The solar system as a living laboratory, our probes now monitor the planets like patients in a cosmic clinic. Juno listens to Jupiter's heartbeat through its magnetic field. InSight measures the tremors of Mars, revealing the slow thrum of its cooling core. Parker Solar Probe dives closer to the Sun than any craft before it, skimming through plasma at 500,000 kilometers per hour to study the origin of the solar wind. Every mission is part of a greater experiment, to understand how systems live, evolve, and interact. In this sense, the solar system is no longer just a collection of worlds. It is an ecosystem. Each body affects the others. Jupiter's gravity sculpts the asteroid belt. Saturn's moons feed its rings. Comets deliver water to barren planets. The sun's storms ripple through magnetic fields all the way to Pluto and beyond. The solar system breathes, oscillates, and responds. It is, in every way that matters, alive not biologically but dynamically. A universe that thinks the instruments we have built, telescopes, rovers, satellites, are not merely tools. They are extensions of consciousness. Through them, the universe has begun to see itself. Every discovery, every image, every equation written on a blackboard is the cosmos reflecting upon its own nature through us. In that sense, humanity is not an accident within the solar system. We are its awareness, a phenomenon that emerged when atoms, forged in ancient stars, learned to question their origin. When we study the planets, we are the universe remembering how it formed. When we search for life beyond Earth, we are the universe asking if it is alone. The more we learn, the clearer it becomes. The boundary between observer and observed is illusion. We are part of the system we explore. The light we capture from a distant moon is the same light that once warmed the oceans of our own world. The next connection, artificial minds and cosmic curiosity. Artificial intelligence now joins us as a new kind of explorer, not of matter, but of meaning. Algorithms scan data from distant probes, detecting anomalies faster than humans could. AI-guided telescopes choose their own targets, following the logic of curiosity encoded by their creators. Soon, our robotic emissaries will not merely follow commands. They will make decisions. Autonomous explorers will map asteroids, dive through alien atmospheres, and perhaps even interpret signals before we receive them. The line between human curiosity and machine curiosity will blur, yet the goal will remain the same: to understand. And when the next generation of explorers, human or machine, looks outward, they will not just see planets and stars. They will see the traces of everything that came before. Every orbit calculated, every signal decoded, every question asked by those who refuse to stop wondering. The living cosmos in the end, the solar system, is not just a physical place. It is an idea, the idea that reality is interconnected, that discovery is endless, and that knowledge grows like a network, branching across time and space. We began as observers of the night sky, lighting fires in caves to mimic the stars. Now we build observatories that capture the birth of galaxies. And still, the impulse is the same: to see, to know, to connect. The solar system, once vast beyond comprehension, has become familiar. A neighborhood we can map, a system we can navigate. Yet the more we understand it, the larger it becomes. Every answer births new questions. Every discovery reveals deeper mysteries. We live in an age where the universe speaks in data, and humanity has learned to listen. Somewhere out there, between the magnetic storms of Jupiter and the frozen plains of Pluto, our machines still whisper across the dark. Each signal they send is not just information. It is intention, proof that curiosity itself is a form of life, and that, through connection, the cosmos continues to know itself. Part 13, the threshold, beyond the solar system, at the outer edge of the sun's influence, where solar winds fade into the vast quiet of interstellar space, lies an invisible frontier, the threshold between what we know and what remains forever uncharted. It is here, at the limit of the heliosphere, that our story meets the greater story of the galaxy. Beyond this point, there is no boundary, no map, no returning light strong enough to illuminate the way. Only distance and time and silence. Yet through that silence, two faint signals continue to speak, the voices of Voyager 1 and Voyager 2. Launched in 1977, they were designed to explore the outer planets. But fate and gravity carried them farther. Their journeys have now spanned nearly half a century, their instruments still alive, powered by the slow decay of radioactive fuel. Each week, they send home whispers, faint, delayed by 22 hours of light travel, yet unmistakably human. Crossing the boundary in 2012, Voyager 1 passed beyond the heliopause, the outermost limit of the sun's protective bubble. For the first time, a human-made object entered interstellar space. The data it returned revealed a sudden change. The solar wind ceased, and cosmic rays from the galaxy surged in. The craft had crossed from the sun's realm into the domain of the stars. For scientists, this moment was more than symbolic. It was a new kind of discovery, not of a place, but of context. The solar system, long thought to be an isolated island, was now recognized as part of a greater ocean. And though Voyager 1 continues to drift outward at more than 60,000 kilometers per hour, it will take another 40,000 years before it even approaches the next star. That scale defies imagination, yet within it lies the truth of our cosmic condition. We are both infinitesimal and significant, fleeting and enduring. Our machines may be small, but they have carried the spark of consciousness farther than life has ever gone. The golden message attached to each Voyager spacecraft is a golden disc, a time capsule engraved with the sounds, images, and languages of Earth. It contains greetings in 55 tongues, music from across cultures, and photographs of life in all its forms. It is humanity's signature on the cosmic ledger, a message cast into the dark, not in expectation of reply, but in celebration of existence itself. Carl Sagan, who helped conceive the record, called it a bottle cast into the cosmic ocean. It carries the laughter of children, the hum of machinery, the heartbeat of a mother and her child. If ever it is found, long after Earth has changed or vanished, it will speak a simple truth, that we once lived, we once looked upward, and we once reached beyond the sky. The golden record is not only for aliens. It is a mirror for us, a reminder that even amid the vast indifference of space, we chose to create something beautiful, to say, this is who we are. The long drift beyond the heliopause, the Voyagers travel into an environment that has no horizon, a place where stars are sparse and the nearest atoms of hydrogen are separated by meters. The sun has faded to a bright star among countless others. The signals from Earth grow weaker, fading into background noise. And yet, those spacecraft endure, still transmitting, still teaching. Eventually, their power will fail. One by one, their instruments will go silent. The last message from Voyager 1 will take 22 hours to reach Earth. And when it does, it will mark the end of an era, the final heartbeat of a machine that outlived every nation that built it. After that, they will continue drifting, perhaps forever. In a billion years, they may pass near another star. If some distant intelligence finds them, the golden record will still gleam faintly, protected by time and vacuum. By then, the Earth will have changed, the sun will have grown brighter, and humanity, whatever we have become, will be a memory written in light. The horizon ahead, yet Voyager's story is not an ending. It is a beginning, the first step toward interstellar exploration. The next generations of probes, concepts like breakthrough starshot or fusion-powered craft, may one day reach the nearest stars within a human lifetime. If we can master the technology to accelerate tiny sails with lasers, we could send fleets of gram-sized explorers to Alpha Centauri, arriving in just a few decades. The dream of reaching another star is no longer fantasy. It is a frontier waiting for courage. It will not be easy. Space between the stars is not empty. It is filled with radiation, dust, and peril. But so was every frontier we have ever crossed. As our technology evolves, we are learning to think in longer spans of time, to design missions that will outlive us, and perhaps to imagine civilizations that think in centuries, not years. The journey beyond the solar system demands not speed, but patience. It asks us to accept that some questions will only be answered by those who come after. The continuum of curiosity standing at the edge of the sun's domain, we see not isolation, but connection. The same gravity that binds us to the Earth also binds us to the galaxy. The same atoms that make our bones were forged in stars that burned long before the sun was born. The solar system is not a boundary, but a bridge, the place where the universe learns to know itself through the curiosity of its children. When we gaze at the faint blue dot of Earth from space, or the golden light of the sun from Neptune's orbit, we are looking at the same phenomenon, consciousness reflecting upon the cosmos. The line between exploration and existence disappears. To explore is to be, and somewhere, far beyond the reach of light, two small machines continue to drift, their antennae pointed homeward, their memories full of sunlight, their golden hearts carrying the story of a world that dared to ask where it came from. They are not lost. They are the beginning of everything still to come.